And also, I thank Dr. Venu for giving such an informative informative inaugural session for us to have the brief overview of our program. Actually, he has explained everything. So let's proceed to the first session, that is from Dr. Shahjahan Sheikh from Yonsei University. Just I will give the brief introduction about him. After that, he will proceed with the session. So it is my privilege to introduce Dr. Shahjahan Sheikh, our distinguished expert speaker for today's first session. Dr. Shahjahan is currently a postdoctoral scientist under the prestigious Brainpool Fellowship in Hybrid Nanomaterial Interfaces Laboratory at the Department of Chemical and Biomolecular Engineering, Yonsei University, South Korea. He is also an invited scientist contributing to cutting edge research in advanced hydrogen technologies. He has finished his BTech in Metallurgical and Materials Engineering from RGKTAP IIIT Nuzivid and MTech from University of Hyderabad in Materials Engineering, later PhD in Chemistry and Green Nanomaterials Research Center from Gyeongbok National University, South Korea, where his PhD thesis really worked on the hydrogen energy and developments. So many outcomes has come from his PhD research, and he is a pioneer in field of green hydrogen and water electrolysis with impactful work spanning AEMW, PEMW, catalyst development, advanced electrodes, and sustainable hydrogen production pathways. His contributions are reflected in his highly prestigious publications, including papers in Nanomicroliters, Advanced Energy Materials, Metals and Materials International, Materials Chemistry and Physics, and many other reputed journals with impressive impact factors. In addition to his academic contributions, Dr. Shahjahan is also an innovator holding patents related to advanced nanomaterial electrodes for anion exchange membrane water electrolyzers, demonstrating his strong contribution to translational research and hydrogen technology development. He has received several notable recognitions, including Brain Pool Fellowship, South Korea, Best Researcher Award, Gyeongbok National University, Brain Korea Scholarship for Research Excellence, Full King Scholarship for Academic Excellence. Dr. Shahjahan's work has significantly advanced the understanding of pure water-fed IAM electrolysis catalyst design and long-term stability improvements, establishing him as an emerging leader in hydrogen energy research. We are extremely honored to have him with us today to deliver the inaugural technical session and also the first session of our FDP program, which is introduction, which is a key to our FDP program, that is introduction to hydrogen energy and global energy landscape. So let's welcome him and let's listen to his talk to have an informative introduction about the hydrogen energy. Dr. Shahjahan, please proceed with the presentation.
Okay, thank you for your introduction. Okay, let's without delay, let's go into the presentation. Uh, just a minute, I will. So my screen is visible, no?
Yes, it is visible.
So my presentation is visible, right?
Yeah, it is visible. Please
Okay.
continue.
So hello, good evening to all. Myself, Dr. Shahjahan Sheikh, postdoctoral scientist in the Department of Chemical and Biomolecular Engineering, Yonsei University, South Korea. First of all, I would like to thank Professor Naidu ji and Professor Bhargavi Rani for inviting me to give the lecture on the topic green hydrogen leading tomorrow's game-changing energy revolution. So these are the contents which I'm going to discuss in further slides. So firstly, I want to give brief introduction about what is hydrogen, why we need it, where we need to use, and how we produce that hydrogen. That I will discuss briefly. And also I will discuss about green hydrogen market in globally and what is the current trend in India. Also I will discuss. And also I will discuss about electrolysis process, which is very important process to produce green hydrogen without emitting any carbon. So I will discuss about that. And of course, obviously I will discuss about my research. Being a researcher, what I contributed towards this green hydrogen energy also I will discuss. So without delay, let's move into the presentation. So what is hydrogen? So this hydrogen term actually comes from Greek. Hydro means water, gens meaning creator. So hydrogen meaning water farmer. So scientists, after discovering that it produced water when it burned or when it used, they gave the name hydrogen. So we all know that hydrogen is the first element in the periodic table, and it is the lightest weight element and most abundant and one of the oldest chemical element in the universe. And it also high clean energy carrier also. So that means when we use it or when we burn it, it produces water by reacting with oxygen. So without emitting impactful impactful gases to the environment, and it is colorless and odorless flammable gas as well. So due to these characteristics, hydrogen is widely using in transport industries, fertilizer industries, energy application, and not limited. It is using in many industries. So, so when we are discussing about hydrogen, it is also very important to discuss about two scientists. One is Henry Cavendish. He is actually British scientist who first discovered this hydrogen when he was doing some experiment. Like when he was doing some experiment with a metal and acids, he observed that some flammable gas was producing. So that he observed that that flammable gas is producing water when it burned. So he felt very interesting. So he gave the name, it is a flammable air. So but he didn't give any name to that, just he gave just one sentence, flammable gas. So this all invent that all discovery happened in 1766. Later, the word hydrogen is given by the scientist Antony Lavoisier. He is also known as father of modern chemistry. So based upon that hydrogen characteristics, he he got that word from Greek and he has given the name as hydrogen in 1783. So he is another important thing about this. Antony Lavoisier is also uh, the he's also gave the name to the oxygen also. Of course, that is not uh, important at this in the presentation. Okay, okay. Anyway, why we need hydrogen? So actually, why hydrogen is availability in the universe a lot. Lot of hydrogen is available, but we are using very small amount of hydrogen, and our daily life or even our transportation energy applications are mainly depends on currently mainly depends on fossil fuels. Of course, fossil fuels emit the carbon to the environment and impacting the environment. So then what we need to do? We have to extract the hydrogen from the universe. So hydrogen in the universe, we have a lot of hydrogen. In other words, we can say infinite supply we can give if you able to extract hydrogen or if you get hydrogen from the environment from the universe. But it always in combined form, whether hydrocarbon form or water form. You have to follow certain method to produce the hydrogen. So here, when you while doing this hydrogen production, if you follow certain methods or green methods, you can produce this hydrogen without emitting any carbon or any unwanted products to the environment. So you can follow safest method to produce hydrogen. So hydrogen has some good characteristics, like it has very high energy density, so that even with a small amount of hydrogen also you can do a lot of work. You can use for a lot of applications. That is one of the advantages. So that is actually attracting the people. And it produces very clean even after using wherever we want to use. It is very safe and it produces very clean clean energy. So we can store a lot of hydrogen also, and we can store for a long time, not a problem. So that is the reason the hydrogen nowadays emerging into many fields like heating, power generation, metal refining, hydrogen vehicles, like that. Many industries, it is one of the important energy carrier. So how hydrogen production takes place, how we produce hydrogen. There are a lot of methods. Among them, these three methods are very important. One is gray hydrogen method, blue hydrogen method, and green hydrogen method. So let's discuss individually what is gray hydrogen method. So the hydrogen which comes from fossil fuels, from natural gas industries or coal industries, we call that gray hydrogen. But during that process, during that hydrogen production, so CO2 is a byproduct that generally released to the atmosphere. So, so that it creates some environmental issues because we have to release CO2, which is coming during the hydrogen production method. So we have to release CO2 to the environment. So that actually creates some environmental issue. But unfortunately, 95% of hydrogen production coming from the gray hydrogen. So another one is blue hydrogen. So blue hydrogen, when we are producing blue hydrogen, the CO2 will come. This blue hydrogen also generally comes from fossil fuels. So during the process, CO2 produced, but this CO2 will not release to the atmosphere. They will capture and store. So that is why compared to the gray hydrogen production method, blue hydrogen production method is somewhat cleaner. But we need to spend a lot of money to store and to capture the CO2 and store the CO2. So two are not that much greenery source. We know that because one is releasing CO2 atmosphere, that is gray hydrogen. Another one is the product which is coming CO2 during the hydrogen production. We have to store that one, and it is costly. Still not gray. It is a blue hydrogen. Now another important is green hydrogen. So green hydrogen. So what is green hydrogen? Actually, while producing the hydrogen, there is no emission of carbon or no emission of any uh, unwanted gases to the environment. So it is very safest green method. So we have to send water to the electrolyzer, do the electrolysis process, produce the hydrogen, and another product will come oxygen. That is also important for the humankind. So zero emission, environmentally very friendly process. So this is actually the important thing we need to discuss. We need to implement. The every scientist or interested in this green hydrogen. So it is actually important to Earth and everybody too. So how this green hydrogen produced? So there is a one process called electrolysis. That process generally occurred in electrolysis system. So that electrolysis system connected to the renewable energy sources for the electricity. Once the electricity happen, electrolysis will happen inside the electrolyzer and separate the water into hydrogen, oxygen, and oxygen, hydrogen will be stored, and hydrogen will be used for different applications. So this is generally we talk about green hydrogen production. So then, what is electrolysis, and why it is important to produce green hydrogen? Let's discuss. So water electrolysis. So it is a process where water molecules split into hydrogen, oxygen under application of electric field. So this entire water electrolysis process happen inside the electrolyzer. In the electrolyzer, there are some materials. One is cathode, another one is anode. At the cathode, hydrogen evolution reaction takes place. From that, hydrogen will produce. In anode side, oxygen evolution takes place. From that, oxygen will be produced. These two reactions combinedly simultaneously happen during the water electrolysis process. So to do this process, there are already well-established electrolyzers are there to do this water electrolysis process. One is alkaline water electrolyzer. Another one is proton exchange membrane water electrolyzer. These two are well established in the industrial scale level. And another emerging electrolyzer, anion exchange membrane water electrolyzer. This is not yet industrialized. It is still in the lab scale. But these two are well established, and these two have their own advantages and disadvantages. Let's discuss individually. So alkaline water electrolysis, shortly we can say AWE. So in this electrolysis technology, the people use very high concentrated KOH solution, like alkali solution like KOH and NaOH to produce hydrogen and oxygen. What is the advantage of AWE? They are very lower cost compared to PMWE. So because we can use non-noble metal as a cathode catalyst or anode catalyst, mostly nickel and nickel Fe catalyst. So that is the reason the cost of the equipment is also very less. And we can maintain in the industrial scale, we can maintain long stability in the industrial scale. So lifetime of the electrodes also very high. So then what is the disadvantage? Disadvantage is production rate. It produces very low performance of the electrolyzer. And we need to use high concentrated KOH or alkali solution. So that obviously we need a very high, we need to take some precautions while using that KOH solution, and we need to store a specific area, specific room, and we have carefully monitor that. So it is like some headache. So that is why the performance wise it is low and cost wise it is best. So it is cost effective but performance wise low. And we need to use high concentrated KOH solution. That is a disadvantage. Now come to the PMWE, proton exchange membrane water electrolyzer. Here the people use solid polymer membrane called proton exchange membrane to split the water into hydrogen oxygen under application of electric field. So what is advantage? It gives very high production rate, high performance, and when you connect this electrolyzer to the renewable energy source, so because we know that renewable energy source is not constant, they always fluctuate based upon depend upon environment, they always fluctuate. So this PMW it well respond to that. That is one of the best advantage of PMW, and it produces very high purity hydrogen production, almost 99.98 percentage or 99 percentage. The purity will be very high. Then what is the problem? The problem is we need to use very expensive material like PT, PTC, iridium oxide, ruthenium. Such a very expensive material you need to use as a cathode catalyst. You have to use the anode material. And even membrane, proton exchange membrane. Generally, people use Nephron type membranes. They are very costly. The equipment cost is very high. So although production, hydrogen production is good in case of PMWE, the problem is we need to use very expensive material. The cost is also very high. So that is the reason this is actually industrial wise the people are using, but they are compromising with the performance and expensive material. So performance wise it's good, but we need to use very expensive material. So that leads to the increasing the rate of hydrogen. Then what is the solution? So So the two are already well established in industrial scale, but AMW is still in the laboratory scale. So people want some alternative because the main researchers or industries or everyone aim is to bring the hydrogen for low cost. So for that AMWE, anion exchange membrane water electrolyzer is one of the alternative for those two electrolyzer. So here in this technology they use anion exchange membrane to transport OH ions from cathode to anode. And by doing a water electrolysis process, they produce hydrogen and oxygen. The advantage of this AMW is low cost material you can use like non-noble metal, mostly nickel Fe based material you can use as a catalyst. So that low cost. Obviously, when you are using non-noble metals, so compared to the noble metal, their cost is very less. And it can be operated with low concentrated KOH solution, even with the pure water also. And it is safe and more environment friendly because we use low concentrated KOH solutions and pure water also we can use. So if you make membrane and electrode assembling properly, MEA means membrane electrode assembling. So this, if you make good membrane electrode assembling, so you can achieve high efficiency, even you can beat PMW performance also. So that means the electrolyzer performance strongly depends upon this MEA designing. So actually that is one advantage and that is also disadvantage. So if you make any good catalyst for this AMW operation, if the MEA design is not good, then performance will be, you have to compromise with performance. So that it is advantages as well as disadvantages. So if you make MEA properly, if you select proper membrane, if you select a proper catalyst, you can increase the performance stability. If not, you have to compromise with the performance. So that is the reason it is not at commercialized, it is not at mature than AWE and PMWE. So it is cost effective and performance both. If you make it, if you make or if you if you make good MEA designing for AMW, and which can give the long stability over 10,000 hours at 1 ampere per centimeter scale. So you can increase the production rate of hydrogen also, so that it can be suitable for the industrial scale. So nowadays people are working on this AMW to bring third alternative for hydrogen, green hydrogen production. Now come to the green hydrogen market. So there are already some electrolyzers are there, they are producing. So India is currently that this actually the data which I'm providing is from different source. So each source is giving different data. So I took from some certain report. So according to that report actually considered in 2023 report. So Indian green hydrogen market by electrolyzer is $22.88 million. So India wants to and expected to grow 69.8 CAGR, compound annual growth rate, by 2032. So India wants to become one of the fastest green energy growth rate. That is India aim. Okay, why we need green? Why green hydrogen critical for India? Because India has very large population country. So we are reaching, we almost all touch, I mean, almost 140 crores we are living inside the country. And many people, I mean, crores of people have their own bikes, own vehicles, and they are they are highly dependent on fossil fuels. So there are a lot of CO2 emitting to the environment, creating very environmental issues. So that is leading to where pollution is very increasing and global warming is very increasing. So it is very risky to the people who is living inside the India. So that is the reason if you take Delhi and Mumbai, some Haryana, the pollution rate is very high. So, so this is actually creating big issue in India. So they must change, they must shift from the fossil fuel to green hydrogen. That is only way we can reduce the pollution. So India is targeting that. So India is actually energy consumer, and it demand will rise 35% by 2030. Oh my God. Then it become too danger, because the energy consumption will rise 35% by 2030. Then if people depend upon fossil fuels, oh my God, the pollution rate very high, then create big issue to the people. So only thing we need to shift our from fossil fuel to green hydrogen. That is the India's aim. So India is targeting by 2070. So India wants to create some country with a green hydrogen, completely net zero emission country. That is the aim. So from different sources, India already getting 66.5 million tons of H2 hydrogen per year at currently. So they are mainly using for refining and fertilizer industries, some energy applications. But we want to use for our vehicles or some transportation, and many applications we need to utilize. But the percentage of hydrogen we have, that is not efficient. And also this 6.5 million tons is actually coming from gray, blue and green hydrogen combinedly. But our aim is to use green hydrogen, so that green hydrogen will be good without emitting, and production of hydrogen also will be good, so no emission. So both will be good. So for that, government brought some policies, especially in 2022, National Green Hydrogen Mission launched to scale the production and demand. So the government of India allotted 2.3 billion. So almost 20,000, nearly 20,000 crores incentive up to 2030. So we are aiming for 2030 and 32. So that policies mainly cover on production, storage, transportation, export infrastructure, etc. So our aim is to produce 5 million tons of green hydrogen annually by 2030. And also gradually we can decrease our hydrogen rate less than $2 per kg in long term. If you keep that aim for long term, we can reduce hydrogen rate also, so that everybody can easily take the hydrogen, they can easily fill the hydrogen in their cars, so that the fossil fuel dependence on fossil fuel will come down. Because hydrogen in the universe, we have a lot of hydrogen. We have very limited fossil fuel in the earth, but we have a lot of hydrogen, but not it is in raw form. We have to extract anyway. So it will some benefit. So India is aiming for that. So when you compare India market or India projects or already well established project, we see. So if you take this blue color, this operational capacity means what is the operational capacity already established in India. This yellow color indicates what is the future. What is future their plans, what they implemented. So when you compare to China and Saudi Arabia, and these are on the top level, but India on 13th position. So India wants to increase more, like India wants to come to top five or top five or top three. India wants to come. So there are a lot of works has to be works and policy has to be implemented. So I think India will do that. So cost wise, India also. So at currently by 2020 it is 4.5. So by 2030 the rate of hydrogen per kg should come under 2.75 per kg euros. So this is actually India aiming for. And currently green hydrogen currently to 2030 target, if you consider, currently we are producing less than 0.86 million tons per year green hydrogen. But we are aiming for by 2030 we are aiming for 5 million tons per year. So we hope we will reach that one. So government will bring new policies. Okay, now come to the global market. So global market $317.12 million according to the 2022 data. So this data can be varied. Different source correlate in different point of view, so that this correlation may vary. So, but that is the reason the same correlation I'm also taking for India, I'm taking for global. So compared to that, the globally green hydrogen $317.12 million. So it is also they want to increase that entire world also increase 65.75% CGR. So currently the green hydrogen coming from green hydrogen coming from electrolysis is 4%. So by 2050 the we are expecting to reach 22. I mean they are aiming for 22%. So now we are highly dependent on fossil fuels, but in future we are highly dependent upon green hydrogen, so that we can protect our environment, we can protect our earth. That is aim. So okay, so being a researcher, so what I contributed for this green hydrogen I will discuss. So already there are well established electrolyzers are there. One is we already discussed, already I explained, alkaline water electrolyzer. Another one is PMWE electrolyzer. This is already well established. They are already using in the industrial scale level. But the two production rate, they are two have their own advantages, disadvantages, and that production rate also varies based upon their operation stability, ability. So we want to bring third electrolyzer to produce this hydrogen, which can balance performance and cost. So AMW is one of the best because it is cost effective, operational simplicity, material flexibility. We can use low concentrated KVH and even pure water also. So we can use a high conductivity membrane which can pass OH very fast, so that we can make electrolysis process easy. But there is an issue. The issue is stability issue and performance issue inside the electrolyzer. Why it is actually happening? Why it is rising? In the electrolyzer, when water electrolysis happen, the gases or some oxygen evolution reaction or hydrogen evolution reaction occur on the catalyst layer. Suppose if the bubbles is freely releasing from this interface, then no problem. So we can use catalyst effectively. AM membrane lifetime also will increase. We will get production rate. But this is not, because most of the electrolyzers are using hydrophobic substrate as a catalyst support. On this substrate, they are depositing or loading the catalyst layer, and they are directly using to the electrolyzer. Then what is happening? So due to the hydrophobic nature of substrate, the bubble accumulation regions happen on the surface of the catalyst layer, which creating dead zones. So they are degrading the catalyst, building the pressure here, and also obstacle the active sites. So exposing of active sites also getting obstruct due to these bubble regions. So that is the reason it is directly impacting the electrolyzer performance, because these dead zones can damage the membrane and catalyst layer. So finally affecting the electrolyzer. Then what is the solution? So if we able to eliminate these gases, if we able to eliminate the dead zones from the surface, from the catalyst layer, the problem will be solved. So electrolyzer performance will be good, AM lifetime also will be good. Then how to do that? So we have to prepare some suprahydraulic substrate or electrodes to the electrolyzer for cathodic reaction, means oxygen evolution reaction, and uh, uh, hydrogen evolution reaction in cathode side and oxygen evolution reaction in the anode side. For both, we can use the suprahydraulic substrate so that we can effectively remove the dead zone, and we can effectively remove the gases from the substrate without forming dead zone formation. So this topic is very interesting. So because many people are concentrated catalyst, but we concentrate on hydrophilic substrates. So based upon that, we kept 3 goals: to produce green hydrogen using AMW. So our goal is we want to use alkaline and pure water based AMW system in cost effective way for sustainable green hydrogen production. That is our first goal. We have to develop one system, AMW, which can be operated with both alkaline and pure water. That is first our aim. Next, we want to improve that AMW performance, developing some advanced electrodes and advanced catalysts, which can effectively use the active sites to enhance the performance of AMWE. And our third goal is to improve the AMWE long-term stability. Not only performance, we want to maintain that AMW maintain long-term the stability. That is another goal. So for that, what we have to do? We have to use hydrophilic electrodes to eliminate the dead zones. So for that, for initially for the anode electrode, we prepared AT&T substrate, anode titanium oxide nanotube substrate, as a superhydrophilic electrode substrate. Then we deposited nickel epic catalyst on AT&T and used as the anode electrode for AMW systems. So how we prepared that nickel epic AT&T? So we took titanium, felt the titanium form from the industry, like from the company, and we did the anodizing to make superhydrophilic electrodes. So after anodizing process, we got titanium oxide nanotubes. We gave the name TNT. So initially it is hydrophobic. In the wettability test we got. After anodizing, we got superhydrophilic. After that, we did annealing. So we got titanium oxide nanotubes, annealed titanium oxide nanotubes. That is also superhydrophilic in nature. Later, because why we did after anodizing, it is also superhydrophilic. Why we did annealing? Because it is amorphous. TNT is amorphous, which is formed after anodizing. It's amorphous and showing low conductivity. Therefore, we conducted annealing to increase the conductivity and crystallinity. Therefore, we attained annealed titanium oxide nanotubes with anatopase. Then we electrochemically deposited nickel epic catalyst on AT&T. That we used as a efficient anode material for the AMW. For the comparison, we also made nickel epic catalyst TNT and AT&T. This is the morphology, titanium oxide nano morphology and AT&T morphology, and initially it is soft. And before and after deposition, both TNT, AT&T maintain superhydrophilic nature. But in case of TF, initially it is hydrophobic. After nickel Fe deposition, it become a hydrophilic due to hydrophilic nature of nickel Fe. Okay. So this is our normal characterizations. This is cross-sectional view of TF and nickel Fe on TF, and this is TN titanium oxide nanotubes before and after deposition. AT&T annealed titanium oxide nanotubes before and after deposition. And XRD analysis also confirmed successful formation of nickel Fe. And HRTM EDS analysis also confirmed that successful formation of nickel Fe nanoparticles on AT&T substrate. And when we analyze individual nanoparticle by cutting using the FIB technique, we observed that the nanoparticle which formed are porous in nature. That is also obviously helpful because porous is there. That is obviously helpful for better hydrogen escape also. So better water electrolysis, better flow of electrolyte, everything will be helpful. XPS analysis also we carried out, which is also confirmed that successful formation of nickel Fe nanoparticle on corresponding AT&T substrate. So after that, once we prepared nickel Fe AT&T electrode, we did half cell measurements initially using 1 molar KVH solution. So also we compared with the remaining electrodes. From the analysis, we observed that nickel Fe AT&T showed better oxygen evolution reaction OER in 1 molar KVH solution, better OER kinetics, better high electrochemical active surface area, better electrochemical surface area based LSB, and better stability. So if you see this stability, this is important, right? If the system is maintained for a long time, that is actually benefit for the hydrogen production. So AT&T based and TNT based, both are suprahydrophilic in nature, already we discussed previously. So these two are maintaining good stability compared to hydrophobic based one. Hydrophobic based one only showed 72 hours. But these two are shown 100 hours. So what is the reason? To find out the reason, we used very high definition camera to capture how bubble releasing happened on the electrode surface. So we used high definition camera. From that high definition camera, we observed that in case of hydrophobic TF based nickel Fe catalyst layer, we observed dead zone formation, accumulation region, which are actually degraded in the catalyst. In case of TNT, this region is less, but still there we can see some dead zones. In case of nickel Fe AT&T, the almost no dead zone has been observed. So that means it effectively removing the gases from the electrode surface and improving the lifetime of the catalyst. So this is a post characterization also is confirming that initially this is the nickel Fe TF based substrate. After 100 hours, after 72 hours, you can see it has damaged. In case of nickel Fe and TNT, initially look like this, but after that there is moderate changes we observe. But in case of nickel Fe AT&T, almost no changes have been observed. And when we did HRTM analysis also using post characterization, we also observed that almost no changes is observed before and after in case of nickel Fe AT&T. And XPS analysis also released the also confirmed that the hydrophobic based catalyst showed higher degradation compared to the hydrophilic one. Nickel Fe AT&T showed lower compared to the remaining two electrodes. So from here we observed that nickel Fe AT&T is showing better performance. Then we went for AMW test. This is actually set up. This is our this is our cathode material, this is our anode material, and this is membrane. This entire, when you make a setup, it become like this. You have to send KVS from one side and KVS from another side, anode and cathode side. You have to connect the heater, and the product will come from this way, hydrogen this way from the cathode side, oxygen will come from anode side. So when we place our nickel Fe AT&T as a anode, commercial PTC at the AT&T as a cathode, we made this AMW setup. So on the AT&T substrate basis setup, this red color one we consider as a hydrophilic based setup. Same catalyst on the TF titanium form, we consider the hydrophobic substrate. When you compare the performance of AMW, we observe that hydrophilic based one showed better performance compared to the hydrophilic one showing better performance than compared to the hydrophobic one. The internal resistance also, we took the ES analysis at different potential at 1.6 and 1.4. If you compare 1.6 and 1.4 in case of AT&T based one, almost no changes in the resistance value. But here you can see the increment resistance because inside the electrolyzer, the bubbles are generating, increasing the they are upstack in the catalyst layer and increasing the resistance. That is the reason you can simply say that hydrophobic one showing higher resistance compared to the hydrophilic one. And better kinetics, better mass transfer we also observed in case of nickel Fe AT&T. The reason, as I said, that dead zone formation. And stability we maintain in AMW almost 1500 hours. Stability we maintain. Still, it is actually we finished. It not a died. It continuously. It went almost over 2000 or 3000 hours, I think. But at 1500 hours, we cut it. Actually, we stopped the experiment due to power issues. So even if we continue, you may reach more than 2000 or 3000 hours. So it is AMW cell is almost doing 1500 hours. So parameters also we studied using different membrane based setup and different flow rates, different temperature effect, and we optimize it by following different parameters so that we observe that piper with a 3 ml at 80 degrees showing better performance than remaining membranes. So this all experiment done by using KOH solution. So same experiments we also carried out by using commercial catalysts also. So same results we observed. So this is actually not important because same trend we observed on AT&T based substrate when you use different catalyst. But this is important, gas efficiency. So hydrogen gas efficiency we observed 79.47% gas efficiency we observed by using this. So we know that AMW cell is very complicated. We don't know what happened inside. So that is the reason we also use transparent electrolyzer to find out how the bubble accumulation region happened inside the electrolyzer, how or what is actually happened within the electrolyzer. So when we use TF based one and AT&T based one, you can see bubble are releasing very and bubble accumulations you can observe. But here almost no bubble accumulation, they are fastly releasing. So from here we observed that AT&T, the super hydrophilic nature of AT&T showing better gas release than TF based one. So once we use KOH solution, later we tried with the pure water also. So pure water with the pure water also we successfully used at to almost we reach 1 ampere per centimeter square and stability 100 hours with the pure water at so it is also good and gas efficiency 60 with the pure water itself we got 63.78. It's actually good. With only nickel Fe we got 63.78% of gas efficiency. This is also very good. And importantly, we also studied how if we use our electrolyzer to the industrial scale, how it respond. Because in the industrial scale, when you connected with the renewable energy sources, we know that renewable energy sources always show some fluctuation. So at that time, the electrolyzer should sustain that fluctuations. So that dynamic loads has to be sustained. So we also tried different our electrolyzer setup with the different potential ranges. One is 0.1 to 1.6, another one is 0.1 volts to 1.8. At different potential we have tried up to different times. So with the different electrolyte DI water 0.1 molar KVA solution, 1 molar KVA solution, we tried different electrolytes also. So we observed that very limited degradation we observed. The positive thing is the electrolyzer didn't die. Usually when you run this kind of experiment, the electrolyzer in lab scale generally die. But here, so it is showing very good performance. It is responding good performance like PMWE. So that indicates it is also best suitable for industrial scale if you make this kind of setup. So after we made that one, we also prepared, like initially we prepared anode material. Later we also prepared cathode one. So in that cathode one, obviously we need to make a advanced one, right? So ruthenium single atom doped nickel, all as an efficient cathode we prepared for AMW. So similar method, electrodeposition method we used to prepare the ruthenium nickel single atom catalyst on AT&T substrate. So similar results, it is hydrophobic and after depositing maintain super hydrophilic, and this results also confirm the successful formation of ruthenium single atom nickel on AT&T substrate. So we also did the off-cell cell measurements, so that is not important to here discuss for time being. So directly we will go to AMW experiment. In the AMW experiment also, when we used already prepared nickel FeAT&T as anode, ruthenium single atom doped nickel AT&T as a cathode, we got better performance than same catalyst and TF based one. So stability also over 1000 hours we observed. Gas efficiency initially that is 79 or 78 with the KVH. Here we got 82.81% with the KVH. So the gas efficiency also increased. And it is also better stability during fluctuations. We also observed with our anode and already prepared cathode. With the pure water also, our gas efficiency increased from 63 to 69.10% with the pure water when we use pure water as electrolyzer. And when we use DI water, we also got better performance. Even at 2, we got more than 1.5. So this is also good. So that means that nickel Fe AT&T and ruthenium single atom nickel AT&T electrolyzer based electrolyzer showing better performance in case of both KVS feeding condition and DI water feeding condition. So, and finally, we also prepared some advanced bifunctional catalyst, which is iridium doped vacancy control CO3O4 catalyst on AT&T. So when we use that catalyst as anode and cathode and only anode, so both are showing better performance than commercial one, better kinetics, better reaction kinetics, better mass transfer, and efficiency almost reached to 87.23% with the KVH solution. And stability both side, if we use same catalyst, it is acting as a bifunctional catalyst, both HER for OER. It is showing better stability compared to the only one side, only anode side catalyst when compared to the commercial one. So it is also stability over 1000 hours is maintained with the KVH solution. With the DA water, also it is almost 900 hours. 900 hours. It is very high with the KVH with the DI water. Both side, if you use same catalyst, it is maintaining 900 hours. It is very good. Performance also, it is almost reaching 1.6 at 1.8. Gas efficiency from 69 to 74.18 we increased with this advanced catalyst with the DI water feeding. So this is actually positive result for hydrogen production. So finally, if you compare our results with already well established already commercial electrolyzers. So commercial electrolyzers around 6, energy consumption is around 6, and this is around 7 point something like that, maybe 7 point like this. But the target of Iran International Renewable Energy shows target to reach 4 kWh nano nm cube. So our setup submit our we set up only one side setup almost beat this one. So we almost achieved this one with these two setups. So it is actually we are almost reached, and we got better result than the target set by the Iranian target. So if you make this kind of electrolyzers, if you develop in case of AMWE, you can increase the performance of AMWE so that you can bring that AMW to the industrial scale level, so that we can bring third alternative for hydrogen production rate. So I think the remaining research also will focus on this AMW to bring that one. So finally, the summary of this presentation. So green hydrogen is very essential for decarbonization and net zero future. That is, we have to give to our next generation. So cost are decreasing and global investments are growing rapidly on this green hydrogen production. So India aims to become major producer and exporter by 2030, especially in green hydrogen compared to the gray and blue hydrogen. And still there are some key challenges remain: cost and infrastructure and renewable capacity. So I hope with the right policies and technologies, this green hydrogen can transfer global energy landscape in future, so that we will achieve net zero future with the right policies and technologies which are required. I think the government will government global governments and Indian government will implicate that one, so that we will reach our hydrogen production less than $2 per kg, so that fossil fuels utilization will be reduced. The people will more interest on hydrogen. So because hydrogen availability in the environment or in the universe is a lot, I think we will make decarbonized uh, earth in future. So these are the research collaborators who are contributing for hydrogen energy along with me from different universities. And these are the publications, state journal publication we published for hydrogen production rates. So which is actually helping for the researcher who actually interested in green hydrogen. This is my publications. It's not that much important. And for the contributing for hydrogen, green hydrogen production, I got some awards, etc. also. So and the news also was published in the university level. Finally, I end up this presentation with a small quote. Obviously, research is very expensive, right? We have to spend a lot of money on research. But suppose if you fear about expenses, if you ignore the research, so you have to cost more in your life. So that means even research is expensive, you must do to reduce cost for the future generation. Thank you for your attention. So any queries you can ask me freely, so I can answer it. Thank you.
Yeah, participants, you can interact. You can ask any questions.
Any queries?
Yeah, we are waiting for the participants. I request all the participants, please interact with the experts.
Hello,
Mhm.
good evening, sir.
Okay.
My question is the what is the difference in the alkaline electrolyzers and the anion exchange? Basically, we are using the hydroxide ion in both the cases. So why
Mhm.
it is more differ? Like why we not say the alkaline is similar to uh, uh, anion exchange electrolyzers? What is the
Uh,
basic? Yes.
So, okay. So, alkali electrolyzer, actually, there are two types of alkali electrolyzer. So, one is alkaline electrolyzer, is also AMW is also alkaline electrolyzer. Okay. So, AWE
Yes.
also in AWE also we need to use alkali solution. So, that is also alkaline based AWE, and in AMW case also we need to use KY solution. So the only difference is here we use anion exchange membrane, so that transfer OH, and you had high conductivity compared to diaphragm. Here we use diaphragm. Okay, diaphragm is like one kind of membrane, but here the people use for OH passing, but conductivity is very less. Okay, so here the membranes is different. So there we use anion exchange membrane, so that anion exchange membrane increase the OH passing. So in case of diaphragm, that OH conductivity path is the conductivity is very less. So that is the only difference. So
Okay, sir.
in both cases, you can use nickel based or whatever hydroxide based you can use.
Yes, sir. Thank you, sir.
Thank you.
Hello, sir.
Yes.
Sir, am I audible to you, sir?
Yes, please ask.
Sir, namaste, sir. This is Teja from Vijayanagaram.
Mhm.
Sir, you said that you have done some research in this hydrogen related topic, right? Sir,
Yes.
the present most concerned thing is about the storage of hydrogen, right? Because generation of hydrogen has been rapidly developing due to some various techniques, but but the real time problem is how to store that obtained hydrogen, right? Sir, instead of I just when on listening this thing, I just got, I don't know why this idea popped up in my mind. Instead of storing that hydrogen energy, why can't we use it readily? Is there any system which uses means there is very little amount of storage and ready-made usage of and అంటే తయారవుతుంటే వాడడం అనమాట, అంటే జస్ట్ లైక్ whenever it is been manufactured or whenever it is been produced by electrolysis process or any other process like thing, it is readily going to be utilized, just like the low pressure acetylene oxygen oxyacetylene low pressure welding system. Just as we drop the calcium carbide crystals into the water, and when the acetylene is released, it has been readily used in low pressure welding systems. Just like that, why can't we use the hydrogen generated readily? Is there any uh, thing? Is there any process which has been developed in this kind of thought process or like that?
So, so your main question is why don't we use directly produce hydrogen without storage? Because your question is, so for storage we need to spend a lot of money and lot of space and lot of issues also. So why don't we directly produce and directly use, right?
Yeah,
So
right, sir.
actually that is good question, but the problem is the hydrogen wherever you, which whether electrolysis process or using any method, if you produce hydrogen, so hydrogen has some purity issues. Okay, so the whatever the hydrogen produced, that is not pure hydrogen. You have to purify it. So for that purification, there is some gas membrane technology is there. So that gas membrane technology, what that is also separate method. What they develop one kind of membranes for there for separation of gases. So initially gas will come, whatever the process, even if you do electrolysis process, even the some oxygen will also be, or some impurities also will be there in the hydrogen. So you will not get 99% of hydrogen. So if you directly use that hydrogen, it creates some hazard issues, you know, right? Because if it is mixing hydrogen, it is not pure hydrogen. So we don't know that how it will react. Okay. So that is the reason people, how after we got, after we store the hydrogen, people generally go for purity checking. So what they do, they generally send to membrane based or some equipment based one. They use some membrane to separate the gases by using permeable method, so that they will produce the gas. So then they will give the grade. So this has some X grade, so you can use for some industry. So this has some X grade can use for this equipment. So like that, based upon grades, they will distribute the hydrogen. So if you say if directly use, then it is create precaution issues. So we cannot use it because just we got the product, we not purified. We not, I mean, we didn't certify it. We have to certify it, then we can use. So if that kind of technology will be developed, like once you got directly there itself, we can separate there itself, we can use that technology will be maybe in the future will be developed. But at this moment, as per my knowledge, now purification certification is most important. So that is the reason precaution issues directly we cannot use hydrogen because the hydrogen which is coming from is not pure. Okay, we have to purify it.
Thank you, sir. Thank you for clarifying the doubt. Thanks a lot.
Thank you. But that was very nice question.
Yeah, thank you, sir. Thank you. Thank you. Sir, can you go to the slide number 20, please, once?
20?
20, sir. 20 or 22. Just 22, sir.
22, okay. So this entire manuscript is available in the, this entire research work is available in the internet. So you can just check it. Rapid outgassing of titanium oxide nanotubes. If you type this one, the entire work will be available in the internet. You can check it.
Thanks a lot, sir.
Hmm.
Thank you, sir. Thank you. Such a wonderful session. Thank you.
Thank you.
Yeah, I think no more questions from the participants.
Okay.
We can conclude this session.
Okay,
I
sir.
would like
Thank
to
you.
express my sincere thanks to the Dr. Shahjahan for giving me that time, and you explained that your research experience about the hydrogen production, and you introduce about the hydrogen to our participants. I hope our participants have well benefited about your session. Uh, as part of the session one, you have given a right introduction to our participants. Thank you very much, sir, once again for your valuable time and your valuable presentation.
Thank you, sir.
Yeah, thank you, sir. Participants, we have some more time for the next session. The next session is going to start by 8 o'clock. Otherwise, I will verify with that next session expert. If he's ready, we can start in another 5 minutes. Is it okay, or we can take some 10 minutes break?
Sir, it is better to take some break, sir.
Yeah, then we will take a break and we'll come back by maybe 7:50, 7:55.
Okay, sir. Okay, sir.
5 minutes before we'll come. Yeah.
Okay. The information will be dropped in the group now, sir.
Yeah, I will. We will drop in the group.
Yeah. Thanks a lot. Thank you.
Yeah. Thank you.